Hello, this is session number 7, I think. And today we'll be talking about the essential element carbon. Now, carbon is not thought of like if you talk to a farmer and ask him, is carbon an essential element? They will probably say no. That's simply because we take it for granted, because you will not find a plant that's deficient on carbon. Why? Because plants source the carbon out of the atmosphere in the form of carbon dioxide. So there's always a supply of carbon. So you don't add it as a fertilizer as such. However, carbon is really the backbone of not just plant life, but also animal life and human life. It's a very, very important mineral, very important element. And this whole thing about organic, what defines being an organic, what doesn't define being organic, all goes back to carbon. So it's really very important. Please bear with me here a little bit, because today's presentation is going to be bordering on the too much scientific line. But I really have to explain these things, for you to understand the importance of carbon and its big role. And why is it the way it is? Okay, now we said in session 2 that matter is comprised of those simple forms, which are the elements. The elements are hydrogen, nitrogen, oxygen, phosphorus, etc. Okay, now these elements are themselves made of atoms. So the atom of any element is the smallest unit that has the properties of all, the entire properties of the element. Okay, you can't get smaller than an atom which has the properties. Now, the atom in itself is comprised of a nucleus and electrons that spin around it. Okay. Now, in the nucleus, there's two things: protons and neutrons. Neutra. Remember, neutrons don't have a charge. Protons have a positive charge. They're in the nucleus, and electrons that spin around them have a negative charge. This is where the origin of electricity actually comes from. Electricity, electronics comes from electron. And it's all based in the atom. The electricity is in the atom. So, the only difference, believe it or not, the only difference between different elements is the number of protons and electrons and neutrons they have in their atom. There's no other difference. So the proton of lead is the same as the proton of gold. There is no difference. The only difference between lead and mercury and zinc and gold and silver is how many protons and neutrons and electrons they have in their atom. Okay? And this is why we have this periodic table. The periodic table lists elements in terms of how many electrons, protons, and neutrons they have in their cells, in the atom, sorry. The simplest one here is hydrogen. Hydrogen has only one. It doesn't even have a neutron, actually. It has just one proton and one electron. And then it goes 2, 3, 4, 5, all the way up to about 100. Now, elements on this side, minerals on this side, are metals. Ones on this side are non-metals. Forget about the ones in the middle. We want to simplify things. Okay? Now we're coming to carbon. Okay, I'm not changing the subject. Now, if you take something here like sodium, which has number 19, what does 19 mean? It means it has 19 protons, 19 neutrons, and 19 electrons. Okay? And you go to the other side, to chloride, or chlorine really, which has 17, its atomic number is 17, meaning it has 17 protons, 17 neutrons, and 17 electrons. The way those two react is by sodium giving an electron to chlorine. It becomes chloride. So the result is sodium chloride, table salt. All right? So that's one way of elements reacting with each other. A giver of electrons and a taker of electrons. Okay? Now that's a chemical reaction. So that's what a chemical reaction is about. Exchange of electrons. As against nuclear reaction, when the reaction is inside the nucleus. We don't deal with nuclear reactions here. Okay. Now, sodium and chlorine cannot react in any other way. When you combine them, they can only form table salt, sodium chloride. If you look at carbon here, I have to be able to see backwards. Carbon has an atomic number of 6. In other words, it has 6 electrons, 6 protons, and 6 neutrons. But instead of being able to either give or take electrons from other atoms, carbon actually shares. It's not the only one that shares. But the difference is that carbon has 4 electrons to share. And it can enter in any number of combinations. Millions. Trillions. You can keep inventing new forms of carbon that didn't even exist in nature. And that's what's so unique about carbon. This is why you have so many chemicals that have carbon inside of them. Okay? You can think of carbon like a gymnast. A young, flexible, nimble gymnast with 4 appendages. You know, you've seen those young gymnasts. You know, they can do the split. They can put one foot here and another foot behind the back, and you know, extremely flexible. 4 arms. It can bend them any whichever way you want. And look at this structure here. Carbon with 4 hydrogens. Okay, you see, those angles are extremely important in molecular chemistry. Those angles are extremely important because normally, again, minerals or atoms have specific angles with which they can bind to other minerals, not carbon. Not carbon. So this simple compound here, it's the simplest of all hydrocarbons. A hydrocarbon is hydrogen and carbon. This is methane. This is methane. But look at those other structures. Now, C is for carbon, of course, H is for hydrogen. Now, these are flattened out. I mean, they're all 3D structures, all of them, but they are flattened out. So you can have, that's again carbon and hydrogen, but here instead of 1 carbon and 4 hydrogens, you have 2 carbons and 4 hydrogens. And you see this dot, dot, it looks like an equal sign. It means there's a double bond. So carbon has to share 4 electrons. Okay, so each of these bonds, except one of the, represents one of those shares. So you got 1, 2, and a double one here, 3, 4. And you see here, the same thing, you have 2 carbons, but instead of having 2 hydrogens, you have 6. And the angles are so different. Look at this one here. This is acetylene. It's C2H2, there's 3 bonds between the carbon, between each other. That's a maverick of a mineral. It's amazing. No wonder there's so much interest in organics. Any whichever way you define organic, because it's all based on carbon. Now this one here, you see, this whole thing doesn't have to be linear, doesn't have to be even branched, because these things can be branched. And that's where the concept of polymers, by the way, come from. We spoke about polymers, about natural polymers before. Because this one here can go on and on and on and on and on and on. You know, like when you fill up your car with petrol, you're filling it up with octane. Octane has 8 of these. Octa is 8. Like octopus, you have 8 carbons. And you make this much, much longer, you start getting into the area of plastics. Now this maverick compound here is benzene. So you see, it's a ring. And each carbon, if you count, because you have a single bond here and 2, so each one has 4. Count them if you don't believe me. Each one has 4. Now that ring, that same ring, actually, can bind to itself. Look at this amazing structure. Any idea what that is? Any idea what that is? Well, this is actually a very, very tiny graphene molecule. You can't refer to it as graphene if it's only this size, really, because you need to have many more rings. But A graphene basically is benzene bound to itself. So it's a single layer of of atoms. That's why it's very difficult to detect, extremely difficult. You can't deal with it. Very difficult, but let's not get into that. Now, if you don't have those double bonds here, you have single bonds, and you have those sheets, then they can bind to each other in a 3D form. And that becomes a graphite. See, it's all carbon. There's nothing else here. We're not talking about like sodium and chloride. I mean, sodium and chloride can combine with each other only in one way. This guy here can combine with itself in many different ways. Actually, this structure can also be spherical. It can be tubular. It's amazing. Well, what about diamond? Diamond is also carbon, only carbon, but each carbon atom is bound to 4 others. And this is only, of course, a very small section of a diamond molecule, if there is such a thing, a diamond structure. And if you expand it all the way, you're going to have bonds going everywhere in each direction. And what do you think that gives diamond? Of course, it gives it that very solid structure, because those atoms are so bound together. They're all single bonds, very strong, and they go in all directions, compare it to that. That's much looser. Now, why am I talking about all of this? Because carbon has such an ability to combine with other minerals and with itself in many, many other ways, it formed a quandary to early chemists. They couldn't understand the nature of those substances they found in living things. So they called them organic compounds, because they come from living things. And there was this notion that they referred to as, gosh, I can't think of the word now. Never mind. They believed that those chemicals that you find in living cells, you will not be able to find in any other form. But then later on, in the 1820s, a scientist by the name of Wolfer was able to actually synthesize oxalic acid from non-living forms. A couple of years later, he was able to synthesize urea from non-organic forms. And that was when this idea of vitalism, I think the term is vitalism, the idea of vitalism started to look obsolete, outdated. So they had to find a new definition of how to define something that is organic. So it's not based on life. So they said, we will define an organic compound as one that has a carbon in it, that is based on carbon. Now, was that definition correct? I don't know. I'm not here to form an opinion. I'm telling you what they did. For fairness, if you want to call something organic, the word comes from organ, it has to be based on life. Maybe they should have called organic chemistry, today's organic chemistry, they should have called it carbon compound chemistry or carbon chemistry. I don't know. I'm not here to make judgment. I'm just telling you what happened. So, there is the ancient definition of what is organic. And that's what people today who advocate organic food, organic production, etc., are still using. Because not many people know about what happened in the world of chemistry. But if you talk to a chemist and you tell him this substance is organic, then his brain is wired differently. He will think of an organic compound, i.e. a carbon.